So our next speaker is Natesh Pillaii. Natesh was a grad student here at Duke and then was a postdoctoral work and is now at Harvard. And I was going to say very nice things about him, but he's actually giving a talk on stuff that I'm not doing with him and stuff that he's working with others. So I'm going to make fun of him and say very nice words. No, it's great to have Natesh back and give a talk. So go ahead.
Hello. Thanks very much for the invitation for the organizers and also a wonderful introduction by Cheyenne. As he said, I just graduated from next door and always good to be home. I also thank you for staying until the last day. So I'll keep my talk relatively short. So I'm, these days, the last few months or so, I've been working in the interface of understanding the phenomenon of statistical efficiency versus computational efficiency in high-dimensional Bayesian estimation. Actually, so let me motivate the problem right away. So the model I'm going to talk about is a very simple model, especially for statisticians. But since there are some other applied mathematicians and computer scientists around, I'd just motivate the model and try to convey one simple result and one simple idea, and I'm happy to chat offline about other things. All right, and this is joint work with Anirban and Devdeep and David Dunson. So Anirban and Devdeep, again, were my fellow countrymen, and they were graduate students at Duke, and now they are at Florida State and Texas A&M. And David has been an inspiration for this all this work. So. So here's the story. So my point is that if you want to, this is a theoretical take on the subject. So my point here is that if you want to rigorously quantify the efficiency of Bayesian methods, an important point is to actually not only characterize the statistical efficiency, but also the computational efficiency of the algorithms in virtually any high-dimensional problems. And surprisingly, this aspect was not understood or realized for lower dimensional problems because of the advent of MCMC and the explosive growth of Bayesian literature in the last 20 years or so. And there's also, most Bayesian methods, as we know, it has a complementary regularization method. You can say that most regularization methods can be considered as some posterior mode or some measure of central tendency of a corresponding Bayesian principle. So, and it's also not quite unfair to say that most regularization methods are extremely efficient in computing one quick point estimate, but to construct an uncertainty estimate around that is virtually still open, and there aren't many satisfactory approaches that actually tell you how to construct that. So you might ask, well, okay, so the Bayesian approaches are complementary, and by construction, they automatically eat posterior high-density regions, right? So if you were to construct an uncertainty estimate, why not run a corresponding Bayesian method, and then there exists Markov chain algorithms, and then you can just report the uncertainty from that, right? So, this entire line of research started by trying to answer that particular question. And you would see virtually everything is open. We only have very few answers, but we do have some rigorous quantitative answers, but it's only the beginning. And I hope I'll convince some of you to actually think further about this. So here's the story. So I was talking to a climate scientist, my colleague Peter Heubers at Harvard, and this is the simple model I said I'd motivate with. So we all know that global warming is happening. So if you look at the temperature, so there are direct instrumental temperatures only for the past 150 years or so. And this is when the British went around and put on little ships and such and put instruments around various parts of the globe, around 2,000 points. And so the number n here is 150. And if you look at the annual mean and you plot it, you can see it's clearly increasing. So what he was asking me was that, okay, well, I want to see whether the spatiotemporal patterns actually change. And in particular, he was interested in quantifying uncertainty because there are a lot of missing data in the early part of the 20th century. So there is uncertainty in that. And in their field, what people usually do is actually they assume stationarity of the covariance matrix, simply take the covariance matrix, and project uncertainty estimates of that. Even in the publicly issued documents by the government actually uses these kind of estimates. And he was genuinely interested in seeing how much these would change if you have a little more sophisticated quantification of uncertainty. So this is the problem. I fit several models for this, and this is one particular model, and for the purpose of this talk. So you can think of this as, okay, let's forget the non-stationarity in time. Let's say we have n is equal to 150, and p is actually 2000. And we want to estimate the covariance matrix. Assume the mean is 0, because you average out, you take the global mean and take the sample mean to be 0. Right? Okay, and this, so statisticians have thought about this. This is a classic model. So what I want to do is, if you're naively to estimate sigma without judicious inclusion of sparsity, you would have roughly order p squared elements to estimate. That's a nightmare. So what you can do is, let's say, okay, well, let's say the true covariance matrix, it can be divided into a residual part and a low rank part. Lambda is a low rank part. And so lambda is a p by k matrix. So it's so effectively, you have to estimate only p times k parameters. And the scientist also had good idea of what k should be. So he said k is roughly less than 10, and there are each k would represent a geographical factor such as the North Atlantic Oscillation or things like that. So that's not very relevant here. All right, so let's assume k is known, and we want to estimate the parameters of lambda. All right. Okay. So, and this is an extremely well-studied model. A lot of, it comes, especially in genomics and lots of other contexts, this is a very extremely popular model. All right, so if you were to construct one-point estimate, what's the simplest solution we have? What's the simplest trick in the book? It also happens to be the only trick in the book. Is that you take the sample covariance matrix, and we know that when p is large, that by itself doesn't work. So what else do we do? You actually construct the sample covariance matrix and threshold the elements. So you would come up with a threshold by very sophisticated methods, but when you have the threshold, you would compute your estimator to be element-wise thresholding. Of course, there are various other versions of this. This is one particularly nice estimator because of its simplicity and the ease with which you can compute this. As far as I know, there is no, so suppose what you're really interested in, a reasonable loss function is the largest eigenvalue, right? So suppose you really want to say, not only do I want the largest eigenvalue, but I also want a reasonable interval around it. And so if you try to use the classical methods to do this, so what are the classical methods? Well, for instance, the bootstrap would perturb the data and try to have a central limit theorem and then have construct confidence intervals based on that. But when p is large, say p is much greater than n, that won't work. And there are lots of, this is an ongoing research area, and I actually don't know what the latest story is. All right, so coming back to the question, okay, so can we actually run a Bayesian method and report uncertainty intervals? If so, what could possibly go wrong with that? So, so here we assume, again, p is to be, again, along the lines of previous talk, we assume p is exponentially in n. Of course, we know that alpha cannot be 1 here because a simple information theoretic argument would tell you that, if the number of predictors grow exponentially in n, then you cannot do anything, right? So, for example, in this class problems, you take the diagonal matrix and perturb every element with order 1. And if p is like exponential in n, information theory tells us that you can't do it. All right. So now to remind you the exact setup, to get a concrete answer, I'm going to make simple things even more simpler. So I'm going to take k is equal to 1. So sigma is of the form sigma squared plus lambda transpose. And so to concretely formulate the question, all right, this is our model, and we have n sample sizes. What is the information theoretic lower bound. So what is the minimum error you must make in whatever procedure you use for this problem? Can we have a Bayesian procedure that actually attains that error? If that's the case, we seemingly, at least in theory, have answered the question we started to answer with, which is actually having a Bayesian procedure which incurs only the minimum error which it must pay, but then after that, it's as efficient as it possibly can be. Fine. I would even argue that a successful answer to this question would be a first gap towards bridging this frequentist Bayesian agreement in this large p small n problem. All right, so now let me tell you why this assumption is slightly different from what is currently used in the covariance literature, because the effective rank, or it's actually full rank because of sigma squared times identity. So it's not a low rank assumption per se, and it's also the effective rank is not small in the sense that the ratio of the trace to the largest eigenvalue is still not very small. But okay, so the first question, the answer to the first question actually is a simple variant of the usual minimax argument. And we can show that actually, yes, indeed, the error you must make for this problem is something like log p n cubed s over n. Well, this is just another error, but the thing you should take home from this is that imagine if Pn is order 1, if P is not large and S is not large, then the error you must make is something like order 1 over root n. And that makes sense because that's what central limit theorem would tell you, that as a sample complexity from simple central limit theorem would try 1 over root n. Now, the log p term would come because of the information theoretic argument I told you, that if you have a matrix with you take a large matrix, covariance matrix, and you perturb the diagonal elements by order 1. If you have p is much larger, you would make an error of order log p. And the powers of log p comes because of the properties of a particular model you would use. What is also interesting is that the parameter s over there, what that is the number of non-zero elements in lambda. So k is 1. So lambda is really a large vector, and we are parameterizing the sparsity by saying the number of non-zero elements, and that's S. All right, so we've answered the first question, right? So the second question is, okay, so how do we choose a prior which attains that rate? So the first candidate, so again, remember the important trick in the book is constructing a covariance estimator with thresholding. So you can look around in the Bayesian literature and say, okay, what is the Bayesian analog of thresholding? And we've heard the answer before in the previous talk. That's actually okay, so before explaining what the prior is, so concretely, what we are asking for is instead of having the point estimate converging to the truth, you observe data and you construct your posterior distribution. And what we are looking for really is what is the rate at which the posterior distribution concentrates around the truth. So this is the point mass priors, the analogs of the threshold, the Bayesian analogs of thresholding. So what they are the following. So we know we postulate that some elements of lambda are 0. So you might as well put a prior on that by postulating with certain probability it's non-zero and with certain other probability it's 0. And if you know sparsity, the number of non-zero elements, the right choice for pi is just S over P. But if you don't know the pi, you can actually put a hyperprior on it. It's basically having any number between 0 and 1. Let's say, and there's for this here, we choose a beta prior. I'll tell you in a minute why that's important. All right. So this is a first candidate, and it makes good sense to try this, because if this doesn't work, then we are really in trouble. Fortunately, it all happens that indeed that prior achieves the information theoretic lower bound that we initially derived. If I have time, I'll come back and see that the proof of this actually really involves novel ideas, but if I have time, I'll come back and tell you what are the ingredients in this. So let's see. So we've taken a concrete model, derived the information theoretic lower bound, and shows a natural prior, which is the analog of thresholding, and indeed showed that for that prior, the posterior achieves the exact rate, the minimum error we must pay but that's it, right? So have we solved the problem yet? And the answer is no, because this is where the promised problem of computational efficiency comes in. What goes wrong here? What goes wrong is that, so of course there's no closed form expression for the posterior, so you have to resort to an MCMC. And the model space is combinatorial because the Markov chain has to explore all the possible non-zero versus zero cases. And that roughly, an easy calculation would tell you that that space is something like, has dimension order of 2 to the power p. So even for moderate p, this doesn't work. Right? So what is efficient? So the only measure, this is another important point, when you have an MCMC algorithm, the efficiency of the algorithms, usually the only way we know how to measure the efficiency, which is useful for practical purposes, is something called the effective sample size. What does that mean? If you run the MCMC, say, for 1 million iterations, it's not obviously equivalent to getting 1 million independent samples from the Markov chain. What happens is that the Markov chain often is heavily correlated, especially in exploring spaces like this. So what the effective sample size is saying is that what is the equivalent independent number of samples that would produce the same variance estimate as that one would get from running the Markov chain for 1 million iterations. Of course, if the correlation is nearly 1, then the effective sample is nearly 0. Of course, the correlation is 0, the effective sample is equal to the number of samples of MCMC you run. All right. So although we seem to have answered the question we set out to, we see that the computational efficiency quickly says, okay, that solution doesn't work. All right, so now what's the next idea? So fortunately, people have been, even though not rigorously theoretically, people, of course, have been working on this problem, and there are partial solutions. Again, nothing theoretically, but partial practical solutions that have been proposed in the literature. So one of them are something called the continuous shrinkage priors. So instead, even though let's say we assume the true model has the true lambda 0 has lots of zeros, but we want to construct a prior distribution for this long vector. But instead of saying they are exactly zeros, because that's what really causing the computational difficulty, right? Because the Markov chain has to go through this combinatorial space, let's relax that assumption and put a continuous distribution. So, and most of these prior distributions that's been proposed in the literature can be unified as follows. So lambda j can be thought of as a Gaussian distribution with for each component has 2 coordinates. One is the psi j, which is called the local scale, and tau is the global scale. So tau is common to all the parameters, and psi j is only common to this particular one. And what these are trying to do, they have 2 different purposes. The psi j is controlling the shrinkage locally for each coordinate, whereas the tau is controlling globally. Now, what's the connection between this and the regularization methods? It turns out that virtually almost all regularization loss functions, which are convex, can be written in this form. For instance, the Bayesian lasso would correspond to tau being, the psi j being double exponential. And I'm using the fact that any symmetric distribution on the unit line, on the real line, can be written as a scale mixture of a Gaussian distribution. All right. So this is just reiterating what I said. We virtually know that almost all regularization methods, the loss functions can be put in this form. So this is the key theorem of this talk. It's almost the punchline. It turns out that most of the global local loss functions I've just showed you, for uncertainty quantification, they actually exhibit suboptimal performance. What do I mean by suboptimal? What I mean by suboptimal is that those priors do not achieve the theoretical efficiency that the point mass priors achieve, which is indeed equivalent to the information theoretical overbound. So that basically quantifies that these priors were introduced precisely for their computational attractiveness, right? And people kind of knew that they need not be completely optimal theoretically, but they're pretty easy to implement. And these easily scale up to about, I don't know, even on a laptop, like 5,000, for instance, which is kind of unimaginable with the other thing. So So this is the key result. So just to conclude that question, okay, so we tried two things. One is the first choice, and the second one is the Bayesian analog of the regularization methods. And it seems that that prior, even though computationally attractive, does not have the theoretical bound. How much time I do have, Cheyenne? Okay. So I want to give you some intuition of actually what goes wrong in this continuous shrinkage prior. Actually, two things there are two ways you can explain what goes wrong. One is an intuitive explanation. I'll tell you what that is in a minute. And then one is a more quantitative explanation. Both are, I think, is interesting. So the first one is actually coming from the lessons we learned from the ideas of James Stein and shrinkage estimation from the 1950s and 1960s. So recall what happens here. So the local global priors, the way we construct a shrinkage prior is basically taking the coordinates and the local scales, which is the psi j, are given IID priors, correct? So what it is saying is that a priori, the prior is giving independent distributions for each of the coordinates. Recall what was amazing about the shrinkage estimation when Stein proposed it is that for efficient shrinkage, you need to borrow information across the coordinates. And what his idea was that if the sample mean for the normal means problem, which does not borrow information across the coordinates, versus this James Stein estimator, which has this norm in the denominator, which borrows information across the coordinates, even if the coordinates in real life, what they represent, have nothing to do with each other, right? For instance, the first coordinate would represent a person's height, the second coordinate would just represent the person's age, or whatever, right? There's nothing to do with each other. And even then, the borrowing information across the coordinates actually makes a difference. Here also, an identical phenomenon happens. And this is really surprising. I've been seeing at least many Bayesians write this in paper, that if you take the Bayesian versions of regularization methods, so the loss functions, say the L1 norm or L2 norm, etc., it will be equivalent to putting independent priors across the coordinates. Now, that would directly contradict the intuition that gets from the shrinkage estimation, where we have to give information across the coordinates. There's one way to quantify that is via a concentration of measure argument. And here's the idea. So the idea, so if you, in Bayesian thinking, if you were to construct a prior, what should you, at the minimum, what should you do? You have to make sure that the prior distribution gives enough probability mass around the truth. Okay? Another way to say that, here the true parameter is lambda 0, and what you want to make sure is that the probability of the prior around the lambda 0 for certain t's are very large, or at least large as possible. So this is my cartoon. Lambda 0 is the truth. You look at a little ball around that, and you want to give a lot of mass to that. The problem is that we don't know what the truth is, so we have to uniformly get an estimate over all the possible values of lambda 0. So here's the concentration of measure argument. So imagine lambda is an element drawn from the prior. If you put independent Gaussians, the norm of lambda is something like a chi-squared. So it's a chi-squared, the mean p with a standard deviation root p. So it actually concentrates heavily, but heavily at the wrong place, right? So we are proposing that lambda 0 is a sparse vector in this high dimensions. And if you draw an element from this prior just we are proposing, it's completely concentrated at the wrong place. Of course, but this is a very simple prior, nobody would use this. But it turns out that all the regularization problems, the corresponding Bayesian priors, exhibit almost an identical phenomenon. It's very hard to see, but this is what's happening. So let me explain. So what's the first prior which we saw, which achieved the lower bound? That concentration around a vector or magnitude of root p is something like much better than what you would get from the previous one. So the previous one is exponentially small in p. bounded above, and the second one is bounded below by something log P. So an order of magnitude improvement in the concentration. And this is actually driving the theoretical efficiency. And just to quickly run through, for instance, I told you that this is not, this is also the feature exhibited by most of the other shrinkage priors. For instance, the Bayesian lasso doesn't improve the concentration much compared to the silly prior I just mentioned about, which is IID normal. All right, so I do have one more slide, and very excited about this. So what's the problem we identified? The problem was that a priori, the regularization priors would give independence across the coordinates. So the first key, then the next natural idea is, okay, what if we induce dependence? So here's the prior. It turns out that, so if you put a double exponential, and you take the local scales and constrain them to be in the simplex. For instance, you take them from a Dirichlet, for instance. If you do that, the concentration of measure again improves drastically. And because, the double exponential is a mixture of Gaussian, we have an efficient Gibbs sampler to sample from this. So to revisit the question, indeed, we actually have a continuous shrinkage prior which achieves the information theoretic lower bound, and it's also efficient to sample from. So final few minutes. So now we have answered the problem. So let me say yes and no. So yes, in the sense that, okay, at least we have something computationally feasible in reasonably large dimensions, which we are interested in quantifying uncertainty. But even now, to have a complete solution of this problem, we have to quantify the running time of the algorithm with respect to the complexity of the sample size and the parameter space. But despite intense research in the MC world, virtually nothing is known to get exact numbers along these lines of how to compare different algorithms. And I wanted to show you something about the HMC algorithm. I'll skip that. And let me close with this slide, which is even in really, really large data sets, the perspective I've just told you, which is basically to compare, to obtain Bayesian methods which obtain the information theoretic lower bound, actually may be too ambitious. Because it is a fact, and almost a back of the envelope calculation, that most MCMC methods would run something like exponentially large in the sample size and the parameter dimension, the ambient dimension, the P. So if you really want a Bayesian method, which is the running time is polynomial, or say something suitable from the computational complexity world, the running time is reasonably fast, then it's kind of, almost naive to assume that there exist algorithms which would achieve the lower bound I just told you. So maybe that calls for a change in perspective, which says, okay, we don't really care about whether you can achieve the best possible lower bound, Bayesian procedures, which is the best possible, but it's actually important to say, if computational time is fixed, how do I evaluate two Bayesian procedures, both in construction of the prior distribution and also in construction of the MCMC algorithms, which would give you the uncertainty estimates? Summary, so again, I hope you've appreciated the importance of computational versus the theoretical efficiency, and we've formulated the problem at least in one simple context and given a simple, reasonably okay answer, but lots more to do. Again, thanks my collaborators for sharing so much time with me, and these results are from 2 papers. Both are available in the archive and my web page. Thanks again.